All right, in this video, we're going to take a look at limits at infinity and talk about, hey, what does that mean? What does that look like? How do we find the limits as x approaches infinity and negative infinity? So let's start off talking about what does it mean if something increases or decreases without bound? So if something increases without bound, that just means that y gets larger and larger to no end, right? Meaning it gets more and more positive, bigger positive number. And then if it decreases without bound, y gets smaller and smaller or more negative to no end. Okay, so it gets bigger and bigger in a negative direction, which is a smaller number. All right, so then down here, when evaluating limits, you are determining what is happening with the y value. Very important, because you're examining what is my y value doing as x approaches the positive and negative infinity. All right, so that's what we're investigating, the y value. Just like before when we did limits, what is the y value when x is this? It's the same idea, but now x is going to positive and negative infinity. So when you write limits at infinity, it looks like this. For example, if you're looking at positive infinity, it's the limit as x approaches infinity is equal to some limit, right? Really, you have three options. Either that's a constant, or 0, or that is also positive and negative infinity. We'll look at how to determine if it's either one of those three options. But then your other one is limit as x approaches negative infinity is also some other limit. Okay. Now that brings us into the idea of horizontal asymptotes, because if you look at this diagram right here, so this is our function, right? Here's our function. And it's kind of like a sinusoid. It goes back and forth, but eventually that function will look like a straight line. Okay, and that is how we get our limit. So right here, this line, this L, just like over here on this L, right here, that represents your limit. And then that ties into a horizontal asymptote, because you can create that line as a function just making it y equals L. And so that's why we bring in horizontal asymptote. So right there, that line that we see in this function, that is your horizontal asymptote. Okay, and that is the same thing as your limit. For your horizontal asymptote, the line y equals L is horizontal asymptote of your function if the limit as x approaches negative infinity is equal to L, or the limit as x approaches positive infinity is equal to some value L. Again, that is your limit, and that would also be your horizontal asymptote. Okay, so let's look at some guidelines for figuring out what your limits are. Rational functions and algebraically how to determine what those limits are going to be. So our rational function that we have here is just x to the n over x to the n. But we're going to look at three different cases. Case number one is, what if the exponent in your numerator is smaller than the exponent in your denominator, right? So for example, if you have x to the second over x to the third, okay, that's an example of this, then the limit as x approaches infinity is going to be 0, right? Because imagine if the value on the bottom grows faster than the value on the top, essentially you have something like this, right? Or a number over infinity, this value is going smaller. If you plug a number, a smaller number over a really, really large number, you'll see that that approaches 0. Now, let's look at case number two. If n is equal to, right, so that'd be what happens if we have x squared over x squared. Well, that's like a number over itself is always 1. So then you would have the limit as x approaches infinity is going to be 1. Or it can be any number, actually, because if you have 2 x squared over x squared, then that would actually be 2. Because the x squared over x squared, that would simplify to 1, but then you would have 2 over 1. Okay? And then case number 3 is, you guessed it, if your exponent in the numerator is larger than your exponent in the denominator. Okay, so you would have x to the third over x squared, or infinity to the third or cubed over infinity squared. That's going to be infinity. This number grows bigger and bigger and bigger, so it grows towards infinity, so it's unbound. So the limit as x approaches infinity there is going to be positive or negative infinity, or it is unbound. Sometimes it could even say it's undefined or does not exist. All right, just kind of depending on the language that they're looking for, it's going to be one of those three answers: positive, negative, infinity, unbound, does not exist. If you're not asked for a specific answer, I would say the best answer would be that it goes towards positive infinity or negative infinity. And the difference would be, like in this example here, it'd be positive infinity, but if that was a negative, then it would be towards negative infinity. Now, you can algebraically look at these. That's probably the easiest way for a lot of them, but sometimes you want to just put them in the graph to make sure. You have to be really careful of the graph that you put it in. For example, right here. Okay, go ahead and pause the video and put this in your graphing calculator, kind of see what it looks like, or use Desmos. Here is what your graph looks like if you were to graph it. And if you look here, this value, these y values are getting closer and closer and closer to 1. It's hard to tell, but it's getting closer and closer and closer and closer to 1, right? So if you're looking at just the graph here, then you would say, well, my answer is as x approaches infinity and negative infinity, my y value approaches 1. However, that's not, in this case, that's not true, because if we look at the table, right, and instead of looking at 2, at 200, okay, it's 1.1. What about 1.6, 20,000, 200,000, 1.99, 2 million, 1.99. Actually, as it increases, it gets closer and closer to 2, right? Because those values are just so big, you just have to be careful. And if you do this algebraically, using the methods above, you essentially take the leading terms right here. So you'd have y is equal to 2x to the third over x to the third. And that, if you put the same number in there, simplifies down to just 2. And so the limit as x approaches, and in this case it's both positive and negative infinity, is 2. And on the graph it looked like 1, but if you go out to larger values, which we can using math here, we see that the limit is actually 2. So just be careful of using finding limits on finding limits on your calculator and using your calculator only. It's into just the defining. This gets really, if you look at the definitions in the book, it gets really confusing. But just know that if you take the limit as x approaches infinity of a function, it can be positive infinity. You can take the limit as x approaches infinity of a function, and you can also get negative infinity. So those are two different outcomes. Again, those are probably the better answers, but sometimes it's also called undefined or unbound. Just be familiar with all of the terminologies around this idea of limits at infinity. Some examples, and I have it set up here so we can look at graphically what does this show us, using tabular methods, that's just the table, what does it show us, and then algebraically, how do we solve this algebraically? Okay, looking at these same problems 3 different ways. So if we look at problem number 1, go ahead and pause this and graph this in your graphing calculator so you can sketch a graph of that said function. It's kind of weird, it looks like this, but again, we don't care what is happening right around the origin. We care about what's happening all the way out at negative infinity and positive infinity as x gets larger and larger, or smaller and smaller. So this is our graph. Right from there, it kind of looks like as x approaches positive infinity and negative infinity, right, it's getting closer and closer to 0. But then if we look at the table, so we're just going to set up a quick table for this one. And if on your graphing calculator, you can, if it's already in there, it'd be really easy for you. You can I started with 5 and then went to 100 and then checked out 1,000 just for those values. Go ahead and pause the video and find some of these values as they get larger and larger to see what your limit is actually approaching as x gets larger and larger. You can see as x gets larger and larger right here, so does your y. Your y is getting, or so it doesn't get larger, it gets closer and closer and closer to 0 actually. Right, so the first one looked like 0, the limit as x approaches infinity, y is 0. The second one does too. Let's look algebraically. Right, and how do we do that? Well, look at the leading terms, and your leading terms are x squared over x to the third. Simplify that down. That simplifies to 1 over x. Now plug infinity in there and you get 1 over infinity, which is 0. So the limit, we know by all three methods, the limit as x approaches infinity is equal to 1 over infinity, which is just 0. Okay, go ahead and do the same thing for 2 and 3. You notice they're a little bit different. Again, looking up at the methods right here. Guidelines. I use 1 for each of those examples. So go ahead and do 2 and 3 here. Graph them. Use the tabular method to find really large or really small values for x and y, and then go ahead and algebraically find them. And then pause it, come back to the video, and then see how you did. Look at number 2 and kind of go through there. The red is obviously your graph and what that's going to look like. And then tabular, if you put in, I started with 2, I don't know why, but you can start with anything. But I went from 2 to 100 to 1,000, and you notice that they're getting closer and closer and closer to that value of 1. So I know that my limit's going to be 1, but algebraically, if we check it, take the leading coefficients, okay, and the leading terms, simplify them down, and it is that leading coefficient, which is 1. So the limit as x approaches infinity, we know is 1. 3 different methods. And then looking at the last one, that's what your graph looks like. It looks like y increases and decreases without bound. If we look at the table, you see as x gets larger, y continues to get larger without bound. And then algebraically, you notice the numerator has a exponent that's larger than the denominator. So yes, as x approaches infinity, so does y. So that would be an example of it increasing without bound. Okay, so let's try this example. On this one, I want you to use your calculator. Remember, look at really large values and really small values to make sure. In this case, it's just large because it's just positive infinity. Go ahead and try this on your own. Pause it, try it on your own, and then come back to the video. Red is our graph, and even if you, using the table, if you plug really large or really small values, you'll see that as x approaches infinity, in this case, it's your y values are approaching and getting closer and closer to 0. And then try this one on your own. You can look at the graph or the tables for this one as well. I decided to do a little bit differently and look at the table, and it's approaching negative infinity, so that's why my x values right here are getting more and more negative, and as it approaches negative infinity, my y values are approaching a single value of just 3, and so I know then the limit as x approaches negative infinity of this function is just going to be 3. So for these, some of them you can use a calculator, that's fine. Actually, some of them would be easier without a calculator, like these examples up here, just straightforward regular rational functions where you can just look at the leading terms, forget everything else because it doesn't matter what happens with everything else. Those leading terms are going to define what happens out as x gets larger and larger or smaller and smaller. So it's entirely up to you which method you use, but on the proofs, like if you did it wrong on the test and you were using the graph, your proof would be to prove that your correct answer now is right using either the tabular method or the algebraic method.